What's going on, everybody? Today we're going to be talking about how to use triple integrals to find the volume of some region. Alrighty, so let's take a quick look at what that means. So if we have a triple integral of some multivariable function, right, and then we're integrating over some region E. Now, if we want to find the volume of E, right, the goal is to find the volume of E. This guy right here, our integrand, is going to be 1. So the triple integral of 1 is going to give you the volume of the region E. Now let's look at what our region E is in this case. We have a cube with a side length of 6. Point A is the midpoint of its edge. That means this distance right here is 3. Let P be the point. Let's let P be the plane that contains points A, B, and C. Okay, and the last part of this question is to find the volume of the cube that lies below the plane P. So we have some plane P. We want to find the volume inside this cube, but under the plane. I also want to quickly preface this by saying that this is not my question. I will be including the source of the question in the description below, as always. Alrighty, so the first thing we want to do with this problem is orient ourselves in space. Where are we in space? And can we put a coordinate? Can we pin coordinates down to A, B, and C? And the answer is absolutely we can. So if we draw a set of axes here in R3, you can see here that we can overlay these set of axes to our cube. What do I mean by that? Well, we'll see here in a second. Okay. So this is going to be our x-axis, right? That lines up right here. And then this is going to be our y. And this is going to be our z-axis. Okay. And this right here is our origin, right? The back end of the cube. Now, you could have placed the origin anywhere. You could have made it up here. But in this case, I thought it would be easiest to place it at the back end of the cube, back left of the cube here. Okay. So now we can pin down coordinates, right, to points A, B, and C. So A is going to be, so we start off at the origin. We move 6 in the positive x, 0 in the y, and 3 in the positive z direction. So 6, 0, 3. Awesome. And B is going to be, right, we start off at the origin. We move 6 in the y, 6 in the z direction. So that's going to be 0, 6, 6. Awesome. Just checking to make sure everything looks good. Okay, and then C is going to be, we start off again at the origin, and we just move up in the positive z direction. As simple as that. No movement in the x or y directions. Awesome. Now we have 3 points that lie on the plane, right? And let's just set up a quick roadmap for what's going to happen. We have these 3 points. Using these 3 points, we can create 2 vectors that lie on the plane P. And after creating those 2 vectors, we take the cross product, we find the normal vector of the plane P, and then we can get the using that information, we can get the equation of the plane. Now, let's create 2 vectors that lie on the plane. So you can choose any 2 points to create 2 vectors. So I'm just going to do AB in this case. So AB is going to be, again, final minus initial, 0 minus 6, 6 minus 0, that's just 6, and 6 minus 3 is 3, right? So that's going to be negative 6, 6, 3. Nice and dandy. Okay, now I'm just, again, picking B and C. Doesn't matter which 2 you pick. As long as you have 2 vectors that lie in the plane, you're going to be able to take the cross product to get that normal vector of the plane. BC, so 0, negative 6, and 0. Perfect. And just to get a quick visual on what we've done here. So if I want to draw my plane. Okay, and I'm only drawing the part of the plane that lies inside this cube. So this is our plane right here. And what we've just done is found 2 vectors that lie in the plane. So AB, right, is the vector connecting point A to point B, and another vector BC, right? We take the cross product of this, we're gonna get the a new vector perpendicular to both vectors A, B, and BC. And that vector also happens to be the normal vector of the plane. So that's exactly the idea here. And that's why the cross product is so useful. Okay, so now we say AB cross BC, and this equals, let's set up our cross product, ijk, and our vector AB, let's put that in, -6, 6, and 3, and BC 0, -6, and 0. Sweet, now let's evaluate this. I times 6 times 0 minus 3 times -6, so that's just going to be 0 plus 18 minus j. 6 times 0 is 0 minus 3 times 0, which is also 0, no contribution from the y component, right, because it's 0 plus k. 6 times 6 is 36 minus 0. That's just going to be 0. And then we can write this like so. 18, 0, 36. Oops. Alrighty, awesome. Now we have our normal vector of the plane. And guess what? We have all the ingredients to find the equation of our tangent plane. Now, just a quick look at what the standard equation of the tangent plane is, where A, B, and C is the normal vector of the plane, right? The normal vector, and x naught, y naught, and z naught, this guy is a point on the plane. Do we have a normal vector? Yes, it is this guy. A, B, and C. And do we have a point of the plane? A point on the plane? Absolutely. We can choose any of these 3 points, right? And we're even told in the question that A, B, and C lie on the plane, right? The plane P contains the points A, B, and C. So we've got all of our ingredients right here to cook up our meal. So let's just go ahead and proceed with that. So A is 18. I'm going to pick the point C because it's easiest, 0, 0, 6. That's the coordinates of that. So x minus 0 plus 0, or yeah, I'm not going to even write that because, again, B is 0, so that goes to 0. And then C is going to be 36 times z minus 6. And all of this equals 0. Now, I am going to write this equation in terms of z, and I will explain why in a second. So let's multiply everything out. 18x plus 36z minus 216, and all of this equals 0. Now we can divide everything by 18, so x plus 2z minus, I believe this is 12, yes, equals 0. And then we are isolating z. We get z equals 6 minus x over 2. Yep, okay. That looks to be correct. Alrighty, now we can go back to finding the volume of E equals the triple integral of 1 dv. Okay, now we need to decide on our order of integration. For this one, I am going to make it dz, dy, dx. Now the order of y and x are interchangeable. I'll explain why in a second. dz, remember how I said earlier that we want to write z in terms of x? Well, this is why, because we're integrating with respect to z first. Now you could integrate with, I suppose, with respect to x first. I thought it would be easiest to integrate with respect to z first. We want to find the limits on z. We want to find the lowest value of z and the maximum value of z. Let's go ahead and establish what that is. Okay, so what is the minimum value of z? Well, we know we want to find right, the volume that lies inside this cube and under this plane. So sort of this space right here. So the minimum value of z, if we think of this bottom of the cube, right, this base as z equals 0, right, that black square that lies inside the cube, z is z equals 0. The minimum value of z is 0, right? We can see that right here. And what is the maximum value of z? Well, z goes from 0 to up to this plane, right? And depending on where you are in the cube, the value of z will change depending on x, which we see right here, right? So if you're starting from right here, from the front of the cube, and you go all the way up until you hit the plane, well, z goes from 0 to 3, right? But if you're back here, then z goes from 0 to 6. So that's why we're expressing the upper bound of z in terms of x. And so the summary of all this, z goes from 0 to the equation of this plane, which is 6 minus x over 2. So z 0 to 6 minus x over 2. All right, now what about y? Let's establish the bounds on y. What is the minimum value of y, right, if we want to find the volume of this region? Well, the minimum value is 0, and the maximum value of y is 6. You can see that right here. That goes all the way to the edge of the cube. Apologies, 0 and to 6. What are the bounds on x? Well, it's the same story. The minimum value of x is 0, and then the maximum value that x can be is 6. So 0 are equal to 6 already. And this is why I was saying earlier that x and y are interchangeable, is because, right, there's regular integers on x and y. And so you could have integrated, the order could have been dz dx dy. I'm just choosing dz dy dx in this case. Doesn't really matter for these two. But z has to come first because it's written, or it has to come before we're integrating with respect to x. Again, because it's the upper limit of z is written in terms of x. Alrighty, so let's go ahead and piece this together. So the volume of E equals the integral from, or we're writing our bounds on x first, right? Because it's the outermost integral. 0 to 6, and then we write the bounds on y, 0 to 6, and then the bounds on z, 0 to 6 minus x over 2 of 1 dz dy dx. How lovely. Now let's go ahead and evaluate this. Now we're integrating with respect to z first. If you notice something cool here is that we don't have any like z terms in the integrand. And also the other thing to note is our lower bound is 0. What does that mean? We can multiply this upper bound by the integrand, and that's your integral. So 0 to 6, 0 to 6, that takes care of the first integral. Now all we have left to do is integrate with respect to y and with respect to x. Lovely. Guess what? Same story over here. The integrand doesn't have any y terms in it, and so we can, and also the lower bound is 0 for this integral. So we can go ahead and multiply 6 by our integrand. That takes care of the integral with respect to y. So that just becomes 36 minus 3x. And all that's left to do is integrate with respect to x. Just going to move down over here. Now this is where we have to do a little bit of work. Not too bad though. 3/2 x squared. Evaluate from 0 to 6. And now this just becomes 36 times 6 minus, let's see, 6 times 6 is 36 times 3 over 2. And you work this out. The answer you'll get is 162. You subtract those and you'll get your final answer, 162. That does it for this problem. Thank you so much for tuning in. Please let me know if you have any questions in the comments below or any suggestions as well. I'd love to hear it on any new video topics or what you'd like to see more of in these videos. Thank you very much. I'll catch you in the next one, and goodbye.